Okay, we're continuing on chapter 7, I think. So last time we got in towards the end there, talking about some calculations. Talking about some calculations that are important and a couple important sort of really conversions and where you get those conversions. So the first one we kind of talked about was Avogadro's number. And Avogadro's number is basically that 1 mole of anything. And that sort of name of a mole, which again, as we talked about last time, is abbreviated as MOL. So once again, when you do see that MOL, it is referring to a mole. It is not a molecule or anything like that. As I mentioned before, usually in chemistry, if they are talking about molecules, they will write out the actual word molecule. So again, if you see MOL, that is a mole, and that's a super common error that a lot of people make, is they do think it means molecule. Just like we talked about that a pair of something represents 2 of something, or if you have a dozen of something, it represents 12. When you say in chemistry that you have a mole of something, it represents a specific number, which is Avogadro's number, and that's the 6.022 times 10 to the 23. Now, the units that kind of go with this, it really does sort of vary. The 2 most common units that you will see are atoms, or they can be molecules. Yeah, those are probably the 2 really most common units that you'll see with Avogadro's number. They could really be any unit along the way. And really, this is just a conversion factor that allows you to convert between moles and atoms or molecules and backwards. So that's also how you know that you maybe need to use it, is somewhere in the problem they do mention something about atoms or they mention something about molecules. That's a really good sort of indication that you probably should use Avogadro's number probably somewhere in that calculation. If you have moles and you want atoms or molecules, you're going to multiply by Avogadro's number. So you'll take 6.022 up on top times 10 to the 23. Again, these could be atoms or molecules up on top, and the mole would be on the bottom. So that's basically the conversion factor that you could get. Remember, you definitely want to make sure you're using your exponent button. Again, just like dimensional analysis here, we're multiplying the top, we're dividing the bottom, the moles cancel, and you end up with atoms. Or again, if you use molecules up there on top, you would end up with molecules at the end. Again, the number would be the same. And obviously, vice versa, if you had atoms or molecules and you wanted moles, you're going to divide by Avogadro's number. So you would take the 6.022 on the bottom there, opposite location to cancel, dimensional analysis, and a mole here up on top. Once again, multiplying and dividing. The atoms, once again, will cancel and you'll be left with moles. So you should really think of Avogadro's number as nothing more than a conversion factor to basically do those 2 conversions. And as I mentioned before, sometimes people want to kind of use the number like in every calculation, and you definitely don't want to do that. So those are the kind of the keywords that you want to look for when you're looking at a problem or you're reading a problem, is again, if any number is given to you in atoms or molecules, or you're asked to solve for something that's in atoms and molecules, again, somewhere along the way, Avogadro's number is really going to probably be used there to do that conversion. Now, probably the conversion factor that we would use the most is molar mass, and we do use molar mass the most. And just a reminder why we use, for example, say atoms versus molecules here. If you were doing something like hydrogen atoms and you wanted moles, we would use Avogadro's number there with atoms as the units per mole. But if you were starting with something like water, which is a molecule, we would use Avogadro's number with the units of molecules. So again, it kind of depends on what you're using it with as to the units that you'll end up with. But here the atoms would cancel or the molecules will happen. But again, the number is exactly the same, whether it's atoms, molecules, pizza, shoes. If you're using Avogadro's number, it's always that 6.022 times 10 to the 23. And you could do it for anybody that's off the periodic table. 1 mole of anything, any element off the periodic table will have 6.022 times 10 to 23 atoms. And you could also do it again, like we see there with water, which is a molecule. For any molecule, if you had water, 1 mole water would represent 6.022 times 10 to 23 molecules of water. Now, like I was just mentioning, really molar mass is probably, again, the conversion factor that you use the most. And molar mass, as we talked about at the end there, has these units, and the units associated with molar mass is grams per mole. And those are the 2 units that are associated with molar mass. Where we find the molar mass is actually exactly where we find the atomic mass on the periodic table. And in fact, the atomic mass and the molar mass on the periodic table are exactly the same number. An AMU per atom will convert into a gram per mole and give you the exact same number that you see on the periodic table. Now you may be asking, why would we use something like molar mass versus, say, just the AMU? And it's just really a logical sort of explanation, which is if you weighed something on a balance, like I said the other day, you typically get that unit in grams, right? So it's just a more usable sort of number than trying to figure out how many AMUs are in grams and all that, when you could just kind of go straight up with grams and use it. So it's just a kind of more usable conversion. And we get the molar mass, once again, like I said, from the periodic table, and it is the number that's on the bottom. And typically speaking, we go about 4 sig figs when we pull the number off the periodic table, because depending on your periodic table, you may have more than 4 sig figs. It depends, but we do pull it out. And when you do pull it out, like you see here, this is basically saying that there are 1.008 grams of hydrogen in every mole of hydrogen. And that's basically this conversion factor, 1.008 grams over moles. And again, you can use it as a conversion factor. Or because it's a conversion factor, you can flip it around, put the moles up on top and the 1.008 grams on the bottom. And again, really molar mass is just simply a conversion factor. Instead of looking it up like in a table, where you go get it is the periodic table, and you basically look it up there. So that's sort of where you find that conversion factor for it. And it's the same idea. This is the main conversion that we go between grams and moles. So grams and moles, or moles back to grams. It's the molar mass that you use as a conversion factor to do so. And if you have grams and you want moles, you're going to divide by the molar mass, put the grams on the bottom, moles on top. And again, same idea, going to multiply and divide. Grams will cancel. You will end up with moles here. If you have moles and want grams, you're going to multiply by the molar mass. And you can take the grams over the moles. And once again, going to multiply and divide. Moles will cancel, going to leave you with grams. That is probably the most common conversion factor that you could have. Just like kind of with anything else, if it's not just one element by itself, but you have a molecule that contains, or a compound that contains multiple elements, you essentially just add up all the parts. So like we did here, we would go to the periodic table and find hydrogen. We would also find oxygen, and you would see 16 there. And again, to get the molar mass here, we just add up all the parts. So remember that the number goes to the element to the left. So that 2 means that we have 2 hydrogens. Each of them from the periodic table has a molar mass of 1.008 grams per mole. And we're going to add it to our oxygen here, that is just one of them. And each of the oxygens from the periodic table is 16 grams per mole. That gives us a molar mass for water of 18.02 grams per mole. And that is how you would sort of say it. If you were asked what is the molar mass of water, it'd be 18.02 grams per 1 mole. The number always stays with the grams part, and it's always per 1 mole. And that's also a really important thing to remember, because as we also talked about in this chapter, we were balancing equations. And sometimes, for example, let's just say we had an equation where there was like a 2 in front of it, and we needed to put a 2 there to balance the equation in front of water. But you needed the molar mass of water. And it's a very common error that people make, is they take that coefficient from the balance equation and incorporate that into the molar mass calculation. You should not do that. So when you are asked for the molar mass of something, it should be based on solely just the actual formula of it. So just the formula, regardless of, say, in a balanced equation, there's like 42 in front of it or something as a coefficient. It doesn't matter. So when you're asked to calculate the molar mass, that is why the definition of molar mass is how many grams there is per 1 mole. And 1 mole would represent just one of the formulas by itself. So when you're calculating molar mass, it does not matter how many the coefficient may be in the equation. It is still just based on the actual individual formula by itself. Any questions on any of that there? Okay. So let's take a look here. So as I showed last time as well, again, you could take anybody off the periodic table. And as we also talked about, I think at the very end last time, the relationship really between Avogadro's number, molar mass, and everybody is, it is really the moles that sort of tie everybody together. So if you had, again, 1 mole of hydrogen, that would equal 1.008 grams, and that would have 6.022 times 10 to the 23 atoms of hydrogen. So the relationship here is, again, that kind of ties all the way across, is if you have to go again from moles to atoms or backwards, that is where you should use Avogadro's number. If you got to go from moles to grams or grams to moles, that is where you should use the molar mass. So again, those are the conversion factors to kind of go all the way across. And if you say I have 1 mole of hydrogen, what you're saying is there's 1.008 grams of it in that 1 mole, or there's 6.022 times 10 to the 23 atoms of hydrogen that's basically there in that particular case. That is why, as an earlier picture, let's see if I can find that picture. It wasn't too far back, I think. For example, here, if we look at all this, these all represent a mole of everything, but they don't look like the same amount of each of those things. And that is because, for example, when we go to the periodic table and we look at a mole of, say, carbon, it has a mass of 12.01, right? Grams represents a mole of carbon. But if you wanted a mole of sulfur, that represents about 3206 grams. If you want a mole of water, that represents 18 grams or so. You know, what it may be. If you wanted a mole of silver, that represents 107.9. So even though they all represent a mole of something, kind of numerically in terms of grams, for example, they do represent a different number of grams for each of those different elements along the way. So as we've been talking about here, really Avogadro's number and molar mass, again, are used as really just conversion factors. And again, that's really what you should think about them as. They're just simply conversion factors. And again, for the molar mass, we just go to the periodic table to grab it. If you need Avogadro's number, it's almost a constant value of 6.022 times 10 to the 23, and that just equals a mole. So those are, again, just the kind of conversion factors you want to use. So why don't you try a couple here and see. We want to know how many moles of helium are in 5.46 grams of helium. If we look on the periodic table for helium, it says 4.003. For the second one, how many grams of zinc are there in 0.256 moles of zinc? And if we look at the periodic table for zinc, it says something like 6538, I guess we'll go with. Okay, let's take a look and see how we're doing. So we're going to take a look at the first one. We got how many moles of helium are there in 5.46 grams. So the first question is, do I need to use Avogadro's number here? The answer is we do not need to use Avogadro's number here because there is no mentions of molecules. There's no mentions of atoms. So again, if you don't have any mention of atoms or molecules, you should not be using Avogadro's number. So this is really just a conversion between grams to moles and backs. So that is our molar mass conversion that we want to use here that we do get from the periodic table. So in this case, we're going to grab it from the periodic table. And again, what that number represents is there's 4.003 grams per mole. That is the molar mass of helium. Again, we could use this as a conversion factor, which means if we needed to, we could flip it around and put the moles on top and the 4.003 grams on the bottom. So again, we're just going to use as a conversion factor. And you just want to kind of keep it simple, like dimensional analysis here, which again means opposites cancel. So I want to get rid of grams, which are on top. I need it in the opposite location, so we do need to flip it in this case. And we're going to put moles of helium up on top and the 4.003 grams on the bottom. Just like dimensional analysis, we're always multiplying the top and dividing the bottom. The grams are going to cancel. And if you do that there, you can take 5.46 divided by 4.003. You got about 1.36 moles here of helium in this case. If you think about it, right, 1 mole of helium is about 4 grams, and here you got about 5.4 grams, so you have just over a mole, right? That's, again, what those numbers represent here in this case. Any questions on that one? Yeah. Yeah, so that's a good question. So in most cases, we don't really look at the molar mass as a conversion factor because kind of the unwritten rule is we take 4 significant figures for it. So I would say in most cases, you're pretty safe just going by the original number there. And that has 3 significant figures, so we'll end with 3. How's that one? Other questions? All right, let's take a look at the bottom one, which is how many grams of zinc are there in 0.256 moles of zinc? Do I need Avogadro's number in this problem? I do not. Again, remember that when you see MOL, that is moles, not molecules. And again, it's a super error, common error that people make. So again, we are doing our kind of grams to moles calculation here. And we would just, again, go to periodic table, and that is where we're just going to get our conversion factor from. And that number, again, means I have 6538 grams of zinc per mole, and that is the molar mass. And just like above, we could flip it around and use it in a conversion factor in the other direction there. And we'll just start, again, think of it like a dimensional analysis problem that we just got to get rid of moles. So opposite location, just like we did in dimensional analysis, if it helps you put a 1 underneath it, and you can see moles are on top. So opposite location, moles on the bottom here. So we're going to go 6538 grams per mole of zinc. Once again, always multiply and then divide the bottom. Here, the moles will cancel. In this case, we're going to go 0.256 times 6538. That's going to give us a 16.7 grams of zinc in this particular case. Same idea here. Yeah, yeah. Are you talking about for the second one, the one we just did? So are you asking, would it be wrong if this was flipped the other way? It would be because it really wouldn't cancel out correctly because you would be multiplying. So what you would have in that case is you would have moles, and then you would, if we just look at the units, moles and grams. So when we would technically be multiplying this, you would end up with units of moles squared over grams, which is obviously not what you're looking for in this case. So it's not necessarily, it's wrong definitely in this calculation because it would not give you the units that you're looking for in this case, since we're looking for just grams, and that's what the only unit that we want to be left with in this case. Yeah. Other questions? So just like the previous one here, in 1 mole zinc, it has about 65 grams. And here we have way less than a mole, right? So we have way less grams. We only have about 16 grams in this particular case. So again, that's what those numbers mean. Questions on that? All right. So why don't you try this one? What would be the mass in grams of 1 gold atom here? And if we look at gold there, it is 197, it looks like. So 197.0 is what we got going on. I heard both answers. I think one of them should be right. The answer that is right is yes, because here we see the keyword we should be looking for, which is atom, right? So if we see atoms are molecules in the problem, Avogadro's number should be used somewhere. In this case, we actually have atoms. So our goal or our pathway here is we're starting with atoms. We want to eventually get to grams. And the thing that really ties those two together is moles. Yeah. So that moles is really what ties it together. So in this particular case, remember to go from atoms to moles. That's going to be your Avogadro's number conversion to do so. And now that you have it in moles, it's now a moles to gram conversion, which is our molar mass conversion. So in this case, we're going to both of them together. The good thing is, remember that really Avogadro's number is a constant. 1 mole of anything equals 6.022 times 10 to the 23 atoms. That again gives you your two possible conversion factors, 1 mole on top, Avogadro's number on the bottom. And here we are using atoms because we're just talking about gold. Or you can flip it around and use Avogadro's number up on top as a conversion factor and moles on the bottom. And a reminder that to get to the molar mass part, we again go to the periodic table to get that conversion. And from the periodic table, what it shows us is in 1 mole of gold, that basically represents 197 grams of gold. And that also gives us two conversion factors that we could use. We could say 197 grams per mole are the mole up on top and 197 grams on the bottom. So again, in this case, much like we talked about with dimensional analysis, we're definitely not going to use all four of those conversion factors. We just want to use the ones that are appropriate in the calculation we're doing. So we're going to start with what was given to us, which in this particular case was simply we are starting with 1 gold atom. And again, to keep it in like dimensional analysis, put a 1 underneath it. That tells us atoms are up on top. And to cancel that, I need atoms in the opposite location. Since I'm doing this conversion right here, I would need that as my conversion factor at this point. And again, we're going to go Avogadro's number on the bottom, 6.022 times 10 to the 23 atoms per mole of gold. If I were to do an answer at this point and kind of stop, what would happen is the units of atoms would cancel and I would actually be in moles at this point, right? And I'm not really looking for that answer, and you could get an answer at this point. Again, as we talked about previously, dimensional analysis, try not to round too strictly here, just keep some digits. But if you want, you could just continue on with the calculation because it's really just a dimensional analysis problem. So we basically just did the first step of the calculation. We can now complete it by using the molar mass here to do the second step of the calculation, which is because I set it up like this, which is why it's important, it should hopefully be very obvious to you that moles here are up on top. So again, to choose the right conversion factor, we need it in the opposite location. So coming to our molar mass conversion factors here, we will need moles on the bottom, and it is this one here that we're going to use in this particular case. And that's going to put 197.0 grams up on top, moles on the bottom. Still doing dimensional analysis, which is always, as we talked about a lot, which is multiply the top, divide the bottom. And now here the moles will cancel. And the only unit left at this point is grams, which is ultimately what we're looking for. So we're going to, as we talked about before, multiply everything up on top, which these are all ones, basically, yeah, except for the last number, which is 197. You don't really need to multiply them by 1 because you'll get 197 at the end. We're going to divide by what's on the bottom, which in this case is really only Avogadro's number, 6.022. Make sure you use your exponent button and a 23. And on our calculator there, we are going to end up with 3.271 and a bunch of other numbers. Remember, do not forget the exponent part, which is times 10 to the minus 22 grams of gold in this case. And again, a reminder that when you do get an answer in scientific notation, like, for example, what I have on my calculator here, mine puts an E and a minus 22. Remember that that E is the times 10 part, so you want to make sure you don't forget it. Again, on some people's calculators, it may just put the number up on top with the times 10, but you definitely don't want to forget the exponent part. Question on that calculation. Again, like I said before, you could split it up, get an answer after the first conversion, and just do the second conversion separately, and you should end up with the same answer at the end of it. Is that a large number or a small number? That's a really small number considering we're talking about one single individual gold atom and what it weighs. And obviously it's to the minus 22, which is really, really small. Any questions on that? Now, in terms of significant figures, we really don't have to worry too much about those in the middle. What we kind of go with on this particular one is That's one. So if you had one of something, it would be probably something that would be considered more like an exact number, a counted number, which remember can have as many significant figures as you want. So in this case, we just took it to 4 based off of the molar mass number there. But you really could have laid it up with any number of significant figures in this case, because it would probably be considered more like an exact number and stuff like that. Any questions on any of that there? All right. So a reminder that we can also do these type of calculations for things that, again, are compounds and there's multiple stuff going on. So why don't you try some here with, say, how many grams are in 0.850 moles of C2H6 in this case. And let's do how many moles are there in, we'll go 3.25 times 10 to the 12 molecules of H2O. So why don't you give that a go? I want to give you some periodic table stuff that might be helpful. We got, I'll do it down here maybe. We got carbon, that's 12.01. Hydrogen, 1.008. Oxygen, 16. The first one, we don't know how many grams there are in 0.85 moles of C2H6. Do I need Avogadro's number in this one? I do not. Again, no mention of molecules, no mention of atoms. So again, this is a grams to mole conversion, and are backwards, right? Moles to grams, actually. And to do that, again, that is the molar mass that we get from the periodic table. Here, we do need to kind of add up all the parts here to get the proper molar mass. So we're going to use, again, the formula here and basically just add up all the parts for the periodic table. So when I look at C2H6, there are 2 carbons. And from the periodic table, each carbon is 12.01. So I'm going to take 2 times 12.01 grams per mole. That is basically going to add up all the mass there for the carbons that are present. I'm going to add it to, we have 6 hydrogens. 6 times hydrogen from the periodic table, 1.008 grams per mole. And that's going to represent the oxygens that are, not, I'm sorry, the hydrogens that are there in that particular case. And that's going to get me 2 times 12.01 plus 6 times 1.008. It's going to give me a 3007 for a molar mass, grams per mole. Remember that this is the molar mass of this compound. It is essentially just a conversion factor. So if we need it like that, we could use it like that, but we could also, if we needed to, in our calculation for a conversion factor, flip it around as well. Any questions on that there so far? At this point, we're ready to kind of set up our problem. We're going to take hopefully a dimensional analysis approach because it will make the decision making a lot easier, hopefully. 0.850 moles of C2H6. Once again, you can put a 1 underneath it just to visually see that the moles are up on top. So remember, opposites still cancel here. So we need the one where the moles are on the bottom, which is that one right there. And we will set it up here with our 3007 grams per mole here, C2H6. Again, because this is dimensional analysis, I always know I'm multiplying the top and dividing the bottom. The moles are going to cancel. That's going to get us here 0.850 basically times 3007. And that will yield us a 25.6 grams of C2H6 as our answer, as grams is the only unit left over, and that's good because we are looking for grams in this case. Yeah. Any questions on that there? Yeah, you would probably be, you should be okay. But just in general, like we were talking about with like the molar mass, pretty much if you're calculating the molar mass, something like this as a compound, or you're just taking off the periodic tables, kind of the general rule is just around that, usually to 4 significant figures is typically what you would do. You would be okay on the calculation if you put 25.5, but just in general, that's generally how molar mass is rounded to 4. Yeah. Other questions? Okay, and in this case, we're going to look at the second one here. We want how many moles are there in 3.25 times 10 to the 12 molecules of water. Do I need Avogadro's number here? I do, because the key word here is molecules, right? And this is going to be a conversion really between molecules and moles. And remember, that is Avogadro's number that we use as our conversion factor basically to do that. That gets us 6.022 times 10 to the 23. We are going to use the units of molecules here because obviously we're using molecules here. And that would be 1 mole of water. That again is going to give us our 2 conversion factors that we could use. 6.022 times 10 to the 23 molecules over moles. Or again, you could flip it around and put moles up on top. And by the way, when nothing's written there, it is assumed that it's 1, basically. 6.022 times 10 to the 23 molecules on the bottom. So that's really all we need for this conversion. So we could set it up. We're going to start with what was given to us, 3.25 times 10 to the 12 molecules of water. Once again, if it helps you, put it over 1. Now, again, shows you that molecules are up on top. Makes, again, the decision-making hopefully a lot easier for you right there. And we want molecules in the opposite location. So we're going to set up here 6.022 times 10 to the 23 molecules on the bottom and 1 mole of water up on top. Again, dimensional analysis, multiply and then divide. So really in this case, we are just taking our 3.25. We want to make sure we hit our exponent button in 12. And we're basically going to divide it by Avogadro's number, 6.022 exponent 23. I think I hit it there. I'm going to try it one more time. Just make sure I didn't miss the number. There you go. And that's going to get us here, it looks like 5.40 times 10 to the minus 12 moles of water in this particular case. Yes. It's really for any unit. The 2 most common units that you'll use it for are atoms and molecules. But it really realistically, like for example, when we say we have 1 mole of something, that basically just represents that number, Avogadro's number, 6.022 times 10 to 23. Like if I said I had a pair of shoes, right? That could represent, right, how many shoes I have. If I had a pair of, donuts, that's how many donuts I have, right? A pair of pencils, that's how many pencils. So the unit with that Avogadro's number, that 6.022 times 10 to 23, could actually be any unit you want. But most commonly, what you see in chemistry is atoms and molecules are the 2 units. And the difference of when we use them is, like on the previous example, we were doing gold, which is just like an element by itself. And if it's just an element by itself, you would use atoms as a unit. But if you have something like water here, or even the top one there, the C2H6, that's more of a molecule with 2 or more atoms together. And that's why we use molecules as the units for that. But the number always stays the same. So that mole basically represents that number, and that number could represent, that many of anything, atoms, molecules, particles, pizzas, shoes, any of those type of things. Yeah. Other questions? Yeah. The original number, again, I would consider that more of an exact number, so you wouldn't have to worry about it. So I would go back to the original number. The one where we had the 1 gold atom. So the 1 gold atom in the original number was 1. So although it's an atom, it would be like if you had 1 pencil, right? That would be something that you would count. and that's considered an exact number, which is something that you can count, or something that's like a definition, like 12 inches equals a foot. So although we can't really visually count it, it's usually kind of considered an exact number in that case because you have one of them basically. So you really could have done as many significant figures on that answer as you wanted to, and it technically wouldn't have been wrong. So if you did only two on that one particular one, I ended up doing four based on the molar mass, which was kind of the other thing that we sort of calculated in that case. Yeah. Other questions? All right. Try one more maybe. Let's see. All right. Let's do how many moles are in 322.5 grams of C6H10O? And let's do how many molecules with that. Okay, let's take a look, see how you're doing. Let's start with the first one here. Do we need Avogadro's number on this one? How many moles there in 322.5 grams? No. So this is again going from grams to moles. That is the molar mass, and that is the periodic table where we get that from. So once again, we're just going to add up all the parts here to this formula. There are, for C6H10O, there are 6 carbons, each from the periodic table, 12.01 grams per mole. That represents our carbons. There are 10 hydrogens there, each from the periodic table, 1.008. That's good to know. And there are 1 oxygen here. It's good to get a lot of rest. And you got 16 grams per mole. And in this case, again, this represents the hydrogens, obviously in that form, and this represents the oxygens. And that's going to get us there. Looks like if we do 6 times 12.01 plus 10 times 1.008 plus a 16, going to give us a molar mass of 98.14 grams per mole. Remember, again, that is really just a conversion factor, so we can use it like that. We could also, if we needed to, flip it around the other way, a mole 98.14 grams. I'm just going to do the calculation down here for number one. So we're going to start with 322.5 grams of C6H10O. Once again, if I put it over 1, I can see grams are up on top, so we do need to use the flip version of it where the grams are on the bottom so that they cancel. We'll go with 98.14 grams on the bottom, a mole of C6H10O. Once again, going to multiply the top, divide the bottom. Grams are going to cancel. So we're basically going to take 322.5 and divide it by 98.14. Going to get us here a 3.286 moles here of our C6H10O. Any questions on the first part of the calculation? Now that we did the first part, let's take a look at the second part, which is we want to know how many molecules would there be in that many moles. Do I need Avogadro's number on this one? I do. Again, the key word there is molecules. So we are going to go from now moles that we just calculated to molecules. And again, that's going to be our Avogadro's number conversion to do that. And again, 1 mole of C6H10O would give you Avogadro's number here, times 10 to the 23. And again, as an earlier question was, in this case, this is not just an element by itself. It is a compound or a molecule. So we do use molecules here as the unit associated with Avogadro's number. And just like any conversion factor, we could flip it around and do the Avogadro's number up on top and the moles on the bottom. So I'm just going to continue on with obviously my answer from the first part, which is halfway through the calculation here. And we're going to go 3.286 moles of C6H10O. And once again, if it helps you can put it over 1. That shows you moles are up on top, so we need it in the opposite location. So we are going to use the conversion factor like on the right here. And we will do 6.022 times 10 to the 23 molecules up on top is a mole. Once again, multiplying and dividing here. Moles are going to cancel. And my equal sign is going to get bigger, apparently. There we go. And I'm just going to actually just use the whole number. So if you used a rounded number, that's okay too. 3.2, actually I'll use a rounded number. 3.286 times 6.022 to the 23. That's going to yield us like a 1.979 times 10 to the 24 molecules here in this particular case. And in 322.5 grams of this compound, you have a lot of molecules. Yeah, and that's times 10 to the 24. That's a ton of molecules moving around, floating around, wherever it may be. Any questions on these calculations here? Grams, moles, molar mass, molecules, atoms, and moles, Avogadro's number. Any questions? Those calculations that we just talked about, in addition to what we talked about at the very beginning of the chapter, we're going to kind of put them together and do calculations from equations and some information that you could calculate from an actual equation. So as we just did those calculations, I would say again, molar mass calculation going from grams to moles or moles to grams is again probably the calculation you're going to use here. You're probably not going to see too much Avogadro's number popping into these type of calculations. It's going to probably be mainly that molar mass, grams to moles or moles to grams. So let's just talk a little bit about an equation. And from a balanced equation, like we talked about at the very beginning of this chapter, we can use the coefficients to represent a certain amount of each of these things in the equation. We could look at the coefficients, and obviously if there's nothing written, it does represent 1 if there's nothing there. And for example, here we could say that there are 2 molecules of H2 react with 1 molecule of O2, gives you 2 molecules of H2O. We could also look at this, and this is really the relationship we're going to use in these calculations. These are what are referred to as the mole to mole relationship. And again, the numbers actually are just the coefficients in the balanced equation. So they just come from the balanced equation, and that's what you get. You can say there are 2 moles, because there's a 2 there, of H2 react with 1 mole of O2, gives you 2 moles of H2O. The bottom one is just the conservation of mass. As we talked about in a chemical reaction, we don't change elements. So if we start with 4 hydrogens on the left, we should have 4 on the right. And again, that's the whole idea of balancing. And since, as we just saw, hydrogen weighs about 1.008 grams per mole, you'll have the exact same molar mass on each side of grams of reactants and products. So what we're talking about here is what's sometimes referred to as stoichiometry. And stoichiometry is a big, scary word, but it really is just a conversion factor. And most things in chemistry are conversion factors. The deal here with this is instead of looking on the periodic table to get our conversion factor, instead of looking in the book or a table to get our conversion factor, where we get our conversion factor for in these type of calculations is the actual balanced equation. So the equation is what we use to come up with the conversion factor, what we want to figure out. The reason we want to know that or need that is in problems, we may be given something where we only know one thing about something in an equation. Maybe we know how much reactants we're starting with, and we want to figure out how much products we're going to make. So we need a way to go from that reactant to the product, and the equation is what allows us to do that. We could also know how much products we form, how much reactants we started with. So if we just know how much products, we could kind of back calculate it. So a conversion factor that comes basically from the balanced equation is really what we're going to be doing here in these calculations. And for us, the units can be really moles and grams is really the units that we're going to see. And a reminder, as we just talked about, that conversion between grams and moles, again, is that molar mass from the periodic table. So again, that calculation we just did comes up in play a lot in these type of calculations as well along the way. Also, extremely important, as we'll talk about, when you do these type of calculations, the very first thing you should always make sure of is your equation is balanced, like we talked about at the very beginning of the chapter. So without a balanced equation, your calculation is definitely going to be wrong. So that should always be like the first thing you think about when you come across these problems is that equation balance? I would say in our case here, if you see numbers, it's probably balanced. But if you definitely don't see any numbers in the equation, the coefficients, the ones in front, you should probably take a pretty good look at it to make sure either it is balanced or you need to balance it like we talked about at the beginning of the chapter. So it's really important, that aspect of it. All right. So really there are four basic steps to these type of problems, and they all revolve around these four steps. The very first thing you want to do is make sure you have a balanced equation. And again, that may require you to balance it, or the equation may just be balanced and given to you, but you definitely want to make sure that you double check. Pretty much automatic, whatever they give you, you need to convert to moles. Now, I would say probably most commonly, that is going to be what we just talked about, our grams to mole conversion, which again would be your molar mass from the periodic table that you would use for that conversion. Mind you, you could have a problem where maybe they give it to you in some weird unit in a problem in the book, but you need to take it from whatever unit they give you to grams and then grams to moles, basically. So, you could have something in pounds that you got to convert to grams, and pounds to grams and grams to moles. But the end part of the second step should always be going from grams to moles. And again, you potentially could have a couple conversions maybe before then, but most of the time it's probably going to be straight up grams to mole conversion that's going to happen there. So basically, we're going to be using it like this: grams on here and molar mass, grams on the bottom, moles on top, right, for our molar mass. And our grams will cancel, we'll end up with moles. So we're going to use our molar mass with the moles up on top, grams on the bottom, and that will get us the moles. The reason you have to do this is when you go to the equation, as we just saw in that previous slide, those coefficients represent the moles of each of those things. So you're then going to actually do the big stoichiometry step, which is go to the balanced equation and find the two things you're interested in. And you're going to find the mole to mole relationship from that equation. If you successfully do step number 3, which is the stoichiometry, you will now be sitting in units of moles always. So if you get to the fourth step, you should definitely be in units of moles. Otherwise, you probably did something incorrect. And the last step is to take those moles and convert it to some other unit. Again, I would say the last step very commonly, but not always, the 100% of the time, is taking moles back to grams is a very common ending step. And that again is the molar mass that we would use. And you would use in the opposite sort of calculation as above. You would start with moles and you would put grams on top and moles on the bottom. And you would do the little calculation and end up with grams at this point. And again, this is the molar mass here. Once again, you could be asked for any type of unit. You could be asked for like pounds at the end, ounces, whatever it may be. But I would say a very common ending is to take the moles and convert it into grams. Trust me when I say that all stoichiometry problems, regardless of how scary the equation looks, the numbers look, they're basically these four steps in order. Do not back up, only go forward in these steps. And what I mean by that is if something is done for you, don't undo it. So for example, if you get to step number 2 and you're starting with moles already given to you, don't unconvert it. right? Back to grams and back to moles, yeah? Just go forward on those steps, yeah? So just continue forward and go 1, 2, 3, 4, and every calculation will basically be those 4 steps. Any questions on that? We're going to obviously do some here in just a second and show you the stuff, yeah. It really does depend on the question. So the number 4 step is, I would say in most cases, you will probably leave the answer in either moles, which means you may not have to do step number 4. You may have to do step number 4 and convert it to grams, which is a very common ending. But honestly, you can be asked to solve for anything at the end. So for example, instead of grams, maybe they want you to go to pounds. So you may have to do a conversion where you take it from moles to grams and then go from grams to pounds conversion. So they really could ask for any type of unit at the end. But the 2 most common you'll probably come across are stopping at moles or going to grams is probably the 2 most common ones, yeah. But technically, they could ask for any type of unit really at the end, yeah. And just like number 2, they could actually give you the number that they give you in any unit. So that's why I said for step number 2 here, it may not be in grams to begin with, but what you want to do if it's not grams is kind of convert it to grams and then use the molar mass to go from grams to moles for step number 2. So that one also could be in technically any unit that they want to kind of give it to you in. Okay. Other questions? All right. So let's take a look at this equation that clearly I just wrote all over. So let me unwrite. Yeah, so if you're doing stoichiometry, so the goal here is really this middle step, as we'll talk about, is this step right here. And because this step right here uses that mole-to-mole relationship, at the beginning part of the calculation, you got to get the number they give you into moles. And then on the back end of the calculation, it really does depend on what they want you to kind of leave your answer in. So if they want you to leave it in moles, you can. If they want you to convert to grams, you have to do that last step or whatever it may be. But leading into step number 3, which is really the stoichiometry part of the calculation, whatever number they give you, it's got to eventually end up in moles before you do that step. Otherwise, because it's really just a conversion, right? So as we talk about with conversions, the only way for units to cancel is they're the same units, right? They got to be in opposite locations. So if you leave like the second step there in grams and then you're coming with a mole to mole sort of conversion, there's no way those grams are going to cancel, right? So they got to be put into the moles before you do the third step, which is a mole to mole conversion, so that when you have moles on top and moles on the bottom, they cancel each other out, basically. Yeah. Other question? Okay. So let's take a look at an equation and first talk about how we could get all these conversion factors from this equation, or how many conversion factors we could actually get from this equation. So remember that really stoichiometry is just a conversion factor, and that is where we get it from. It's the balanced equation. So that's why the very first step is always to make sure that you have a balanced equation. Otherwise, you will be doing this calculation incorrectly. So from this one equation here, we could actually get a number of equalities. So remember, just basic equality, right, gives you 2 conversion factors to choose from, right? Equality, 2 things that are the same, that are in different units. And we could get several, and they're all going to come, and people always kind of get this kind of confused. They think it comes from some weird location. Everything in terms of these relationships are all coming from the coefficients from the balanced equation. So that is where we're getting all these numbers from. And remember, again, if nothing is written there, as I said a second ago, it does represent that there's 1 of something. For the O2, there's basically 1. And each of these relationships here, or each of these coefficients, can be thought of as the moles of each of those sort of guys. So if I look at this equation, I can see that for every 2 moles of CO, how many moles of O2 would I have to put in there? 1. Yeah, so equals 1 mole of O2. That's an equality that I could get from this equation. That's an equality that will give me 2 conversion factors that I could use in the calculation. And just like any conversion factor, it's just a fraction, right? So we could write there are 2 moles of CO over 1 mole of O2. Or we could flip it around just like a normal conversion factor, do 1 mole of O2 over 2 moles of CO. So just from that one sort of equality from this equation, we have now 2 conversion factors available to us to use in a calculation. Now, if I look at this equation, for every 2 moles of CO I put in there, How many moles of CO2 do I get out? I get 2. That gives me another equality that I could get from this equation. For every 2 moles of CO, I get 2 moles of CO2 out. That again is going to allow me to have 2 more conversion factors I technically could use in the calculation. I could have 2 moles of CO up on top, 2 moles of CO2 on the bottom, or flip it around, 2 moles of CO2, 2 moles of CO. So again, these are our conversion factors, right? And these are our qualities we could get from the equation. But I'm not done, because I also can see that for every 1 mole of O2 in this case, I get how many moles of CO2 out? 2. Yeah. Which again is going to give me an option of 2 more conversion factors that I could use. 1 mole of O2, 2 moles of CO2, or flip it around, 2 moles of CO2 gives me 1 mole of O2. So from this one balanced equation, it allows me to basically have the option of using 6 different conversion factors just from this one equation. Will I use all 6 in the calculation? If you do, you're definitely doing it wrong. Yeah. You're just going to pick probably one and one only. And again, you're going to use the one that you need. And the way you figure out which one you need is, again, just thinking about dimensional analysis, opposites cancel, right? Now, sometimes people are confused about the idea that that says 2 moles of CO equals 1 mole of O2. This is not equal to each other in terms of numbers. These are equal to each other in terms of like proportion you need in this equation of each of those things to get this equation to happen. Like if you baked a dozen cookies, you need so much flour, right, to be tossed in there with so much chocolate chips and butter and all that stuff to give you like 12 cookies at the end. If you're making big ones, maybe 24 if you're making little smaller ones. But that's the proportion of everything that needs to come together. So when we say in this case that 2 moles of CO equals 1 mole of O2, we're talking more about the proportion of those guys that need to come together to produce the products, not that like 2 equals 1, obviously, in this case, or anything like that. Any questions on that there? All right. So as I mentioned before, people get really concerned about stoichiometry, but it really is just a conversion factor. And again, it's that balanced equation that is where you get those conversion factors from. This is also, hopefully you could see why it's really important that the very first thing you do is balance the equation. Because if I did not balance the equation, had no numbers there, all my conversions are going to be a one-to-one conversion, right? Which is incorrect in this case. So that's always why you want to make sure you balance it. So how do we use this? Let's just say, for example, that in this particular case, I produced, we'll go with 12.1 grams of CO2 in this reaction. And I want to know how much O2 did I start with. So I want to know how many grams of O2 did I start with. Okay. So we're going to do this, and I think I'll do it up here so it'll be a little bit higher here. I think, get rid of that there. So we did, wait, 12.1, right? So we got 12.1 grams of CO2 produced. And we want to know how many grams of O2 did we start with. All right. So we're going to start with the 4 steps, which is we want to balance the equation, which obviously here it is already done, so that's pretty good. So that's pretty straightforward. So step number 1, balance the equation. Step number 2, if you remember the 4 things that I put on there, is to take whatever they gave you and you need to convert it to moles, right? So step 2, after we balance the equation, step 2 is to convert to moles. Do I need to do that in this case? If I'm starting with 12.1 grams of CO2, do I need to convert that to moles? I do, because grams are not moles, right? So because of what they gave me was in units of grams, I need to convert them to moles. I could do that, right? Because that's the calculation we just were doing, right? So why don't you take a look at it? We're going to use the molar mass to do that, right? Carbon 12.01, oxygen 16, right? So here we would need the molar mass of CO2. So if we take a look at the periodic table, we see carbon is 12.01 grams per mole for the one carbon. There are two oxygens, each are 16, as we just did in the previous calculations. You add that all together, that's going to get you a 44.01 grams per mole. That again is the molar mass, which is our conversion factor to go from grams to moles. And again, we could use it just like that with grams on top. We could also, like we were talking about, if we needed to, we could flip it around and use it with the moles up on top, right? Moles is 44.01 grams. By the way, as I mentioned earlier, I just calculated the molar mass of CO2, right? Did I do anything with this number? I did not. So again, when you are calculating molar mass, it is based just on the formula, CO2. Again, people, when they go calculate molar mass in these type of problems, will see the 2 in front of it, and all of a sudden multiply their molar mass by 2, and you shouldn't do that. So again, the proper molar mass for CO2 is just based on the CO2 formula, regardless of the coefficient that we see in the equation. And now we could do our conversion. We're going to convert our 12.01 grams into moles, doing our step number 2 here. So step number 2, we're going to take our 12.1 grams of CO2. And again, we're going to put it over there. And we have this as our option for step number 2, 4401 grams per mole. Or a mole is 44.01 grams. And again, we're going to just keep it simple and go opposites cancel. So in this particular case, we need grams on the bottom, which means we do want to use it in this form here. We'll end up with 4401 grams of CO2 per mole of CO2. This again is the molar mass from the periodic table, just like we did in all those calculations before the break, right? We're going to multiply up on top. We're going to divide by the bottom. The grams are going to cancel. That's going to give us 12.01 divided by 4401. I just did carbon. That's bad. 12.1, geez, right number there. 12.1 divided by 4401. Try that number. That's going to give us 0.27494 moles of CO2. So this is the second step in any of these type of calculations, which is whatever number they give you, you got to get it into those moles. Yeah. First off, any question on that calculation there? I'm not going to round too much because I know I'm going to take that number and kind of continue on with the calculation here. So I'm not going to do any really strong rounding here. Now, this is really where the stoichiometry part comes into play. The reason we need the stoichiometry part is what are we ultimately interested in this case? Are we interested in CO2? We are not. We're ultimately interested in what thing in the equation? The grams of O2. So we need a way to now take our moles of CO2 and convert them into moles of O2 because that's what we're actually interested in. We don't really care that much about the CO2. We need to get over to the O2. And that is where our equation comes into play. We're going to look at CO2 and we're going to look at O2 and we're going to find the mole-to-mole relationship, which we did earlier. And we could see from the equation, it is this one right here. That is the relationship that we get from the equation. And that gave us an option of 2 conversion factors to use. That means in this particular problem, we could care less about the other 4 that are up there. We only need to worry about these 2 because those are the 2 things we're interested in, which is the CO2 and the O2 in this case. And if we take a look at where we're at this point, we're going to go to the mole-to-mole relationship from the equation. And we see that from the equation, for every 2 moles of CO2, we get 1 mole of O2. And again, that is the coefficients in the equation that we did earlier. And that's going to give us 2 options for conversion factors. 2 moles of CO2, I'll just write on this page so we can see it. 1 mole of O2 are 1 mole of O2, 2 moles of CO2. So if we continue on with our calculation, we have 0.27494 moles of CO2. I want to get rid of CO2. Should I use a conversion factor on the left or on the right in this case? Which one would put CO2 in the opposite location? Yeah, the one here over on the right, right? So it's on top. I'm going to use it. Do not blink. This is the big stoichiometry move right here. It is this conversion that I got from the equation. That is basically what we're doing here. This is coming from the balanced equation. And we're going to, again, multiply on top, divide on the bottom. The moles of CO2 will cancel, and we'll divide that number by 2 in this case. And this will give us 0.13747 moles of O2. That is the big stoichiometry move. It allowed us to go from CO2, which was the only piece of information we knew, to O2, which is really what we're interested in this case. And it is the conversion factor that we get from the equation that allows us to do that. Questions on that there? If we were looking for our answer in moles, what should we do at this point? We should round that up a little bit to the right number and put a box around it, right? We potentially could be done if we were looking for moles. But in this case, we're not looking for moles, right, for our final unit. We are looking for grams, which means we will do the 4th step at this point, which is take those moles and we're going to convert them into grams. In order to do that, if I need to go from moles to grams, what do I need? I need the molar mass from the periodic table. At this point, what molar mass do I need for what thing? I need it for O2, right? Because we are no longer doing any CO2 at this point, right? We converted away from it. So we need O2, which means I would go to the periodic table and look at my oxygen, and it will still say 16, I hope. And from the periodic table, that is 2 times 16 grams per mole. That will give you 32 grams per mole for our molar mass of O2. Remember, it is just a conversion factor, right? So taking our number from here, from the previous step, 0.13747 moles of O2. Again, opposites cancel. I need to use it actually the way it's written with the moles on the bottom, so it's in the opposite location. Gives me 32 grams per mole of O2. And again, still multiplying and dividing here, right? So why it's important to set it up as dimensional analysis? Because you should always know the math you're doing. Multiply the top, divide the bottom. Again, keeping it as simple as possible without having to think about too much in terms of math of what's going on. We're going to multiply by 32. This is the end of the calculation, so at this point we can round, and we will end up with moles canceling, and we'll end up with like 4.4 grams of O2 in this case. And those are the 4 steps in this case. In this case, we had to do all of the 4 steps. Sometimes you may not have to do all of the 4 steps. Basically, what this number represents is, in this particular reaction, if you tossed in there 4.4 grams of O2 and everything went perfect, you should get out 12.1 grams of CO2 in this reaction. Nothing bad happened, didn't drop anything, no side reactions. In an ideal world, if you put in there 4.4 grams of O2, you would actually produce 12.1 grams of CO2. That's basically what these numbers represent. First off, any questions on those 4 steps there? Now, sometimes people think when they look at this that in terms of relationships, that you always have to, for example, do the relationships across the arrow, and you do not. So you could do the relationships like we did across the arrow. You could start with products like we did this time and end with reactants. You could start with reactants and end with products. You could stay on one side of the reaction without even crossing over and just do the relationship between the two reactants. Although in this reaction, we do not have two products, but if we did have two products, you could also do that same type of relationship with just the products. So you could go across the arrow either way. You could stay on one side of the arrow and do these type of relationships here along the way. Any questions on that there? So why don't we try one here? Let's say we had this equation. So let's say we got a little N2 plus some H2 goes to a little NH3 action, a little bit of that there, a little bit of that there. And let's say that we started with, we'll go with 5.65 grams of H2. How many grams of NH3 would you produce? So give it a go, follow those same 4 steps. You want to balance the equation. You want to convert to moles. You want to do the mole to mole relationship. And you want to take moles to some other unit. All right, so take some time here and see what you come up with. I'll give you some numbers. Hydrogen from the periodic table 1.008, nitrogen 1401, and I think that's it. Nitrogen. Yeah. All right, give it a go. Again, follow those steps in order. Something's done for you, go forward. Don't go backwards. See what you end up with. Bless you. Bless you. Always is a balanced equation. So if you go through that, you should hopefully recognize that it is balanced, and that's good. So we don't have to do anything there. So that is done. Step number 2 is to take whatever they gave you, which in this case is 5.65 grams of H2, and convert it to moles. Do I need to do that? I do, right? So again, that's just simply a grams to mole conversion, which tells us that we do need to get the molar mass here of, in this case, H2, because that's what was given to us. So we would go to the periodic table there, right? And for H2, it is 2 times 1.008 grams per mole. And that is the molar mass, 2.016 grams per mole. Once again, we do not incorporate that 3 into the molar mass. So it is just based off of the H2 formula. We're going to use that really as a conversion factor. So we're going to start with what was given to us, 5.65 grams of H2. We'll pop it over 1. We could hopefully clearly see grams are up on top, and we want to get rid of them. So we would need to use this molar mass in the opposite way and put the moles on top and the grams on the bottom is the proper way that we need to use it as a conversion factor. That puts everybody in the opposite location that needs to cancel, which in this case is the grams. So we multiply, we divide, grams will go away, and we will end up with 5.65 divided by 2.016. And that's going to give me 2.803 moles of H2. Any question on that calculation there? The really whole purpose of doing step number 2 is for the stoichiometry part, because number 3 is the mole to mole relationship. The reason we need to do this is, are we interested in H2 for our final answer? We are not interested in the H2, right? We are interested in the NH3. So we need a conversion factor to get rid of the H2 where we're currently sitting and get ourselves over to NH3. And that is what the stoichiometry and the mole-to-mole relationship is going to do for you. So if we go to the equation, from the equation, how many moles of H2 do I see in that equation? H2, I see how many moles? What's the number in front of it? 3. This number right there. So I have 3 moles of H2. How many moles of NH3 do I have from the equation? It is 2. Again, the coefficient that is in front equals 2 moles of NH3. That's our equality. And again, from that, we could get 2 conversion factors. We could get 3 moles of H2 over 2 moles of NH3 are 2 moles of NH3 over 3 moles of H2. Once again, we're going to continue on with our H2 from previous step. We got 2.803 moles of H2. Again, we can see moles of H2s on top, so we want to get rid of them. I should use the conversion factor on the right, opposite location, right? Place that H2 on the bottom. This is the big stoichiometry move right here. 2 moles of NH3. 3 moles of H2. Again, from the balanced equation is where that comes from. We're going to multiply and divide. Moles of H2 will cancel. And we're basically going to times that 2.8 number by 2 and then come back and divide it by 3. And that will give me 1.868 moles of NH3. If I were looking for moles of NH3, my calculation would be done at this point. I could just put a box around it, basically, clean up the significant figures probably, but that would be the end of calculation. But we are not looking for moles. We are looking for grams, right? So we do need to get to the fourth step. And really at this point, we are in moles, which you should always be in at this point. We need to now convert it to grams. And again, to go from moles to grams, it is the molar mass conversion that we need to use. So we'll go 4 here. We're going to go moles to grams in this case. And we will need, the important part though, right, is we are no longer on H2. We are now on NH3. So we have to then calculate the molar mass of NH3 from the periodic table. And if we look at it there from the periodic table, we have 1 nitrogen at 1401, and we got 3 hydrogens at 1.008 grams. That's going to give us a 1703 gram per mole as our molar mass conversion factor to go from moles now back to grams. So the last thing we're going to do is take the number we had above, 1.868 moles of NH3. We actually are going to use it just like it's written, grams up on top, so they cancel. So 17.03 grams per mole of NH3. Again, multiplying and dividing. Moles are going to cancel, and we will be left with here 17.03. At this point, we could round pretty much based off of this number, which is 3 sig figs, to 31.8 grams of NH3 in this case would be our final answer. And basically what that represents is if you did this reaction, you put in there 5.65 grams of hydrogen, everything went perfect in this reaction. The most amount of NH3 you could get out is 31 grams, 31.8 grams of it would get out there. Again, the same 4 steps, just keep repeating them, and you should get to the end there at the end of the calculation. Any questions?